welcome to the last day of the school. And today's first session will be given by Gabriele Perfetto. Over to you.
Okay, hi. Thank you, everybody. It's the last day, so I know it's difficult for everybody, even though it's still morning. So I will try to keep it, let's say, light and to draw some final conclusions about what we saw in the previous three lectures. And then after the break, we have a tutorial, and in the tutorial, we will see some specific cases, some exercises, or some evaluation of this kind of formulas, theories for some specific concrete model. Okay, just to start with the summary, last time we finished the part about the thermodynamic description of integrable systems, and we derived a set of coupled nonlinear integral equations, which are what are known as thermodynamic Bethe-ansatz. In particular, we have seen that the free energy density, which is this lowercase f, can be written in terms of an integral over the asymptotic momenta. I'm dropping the minus infinity just for brevity, of a free energy per unit mode, which is dependent on the statistics of the particles. This is what we saw last time. So for instance, this is for classical fermions and bosons, which are standard free energy function of classical fermionic or bosonic particles. Important point is that you see this is like the free energy of a free system, because it integrates over momenta, the free energy function of a single momentum. The crucial point is that this epsilon here, this energy here, is not the one of a free system, because it's dressed by the interaction with all the other particles due to the scattering that a target particle with momentum p accumulates due to the interaction. In particular, you see that this WP, we saw it is something like that. So it encodes the information about the chosen initial state, so the inverse temperatures, and these are the single particle eigenvalues for the ith conserved charge. And you see that this epsilon is the bare value dressed by this part here, which fills the scattering shift phi. Okay. And then we defined also dressing operation. Just write it because this will be useful for today. The dressing operation for a generic function of the momenta. Okay, rho t is equal to this. This is just a summary of what we saw last time, but I write so that we have everything more or less in a single blackboard. Just notice, just one comment, I'm taking here a different convention because with the 2 pi factor, because I realized that, as some of you told me last time, there was some inconsistency. I checked it and I revised. I also revised the notes so that I will upload on the website the new updated notes so that you have revised. So the 2 pi, it's here, so that this n is defined this way, and there is no 2 pi here in the dressing operation, apart the one that is in the integration measure. And we saw that there are 3 important densities. So there is this one here. This is a row of subscript particles. So this P here, the subscript stands for particle. So this is density of particles in the phase space with momentum P. This is the total state density. This is why there is a subscript T. And this n is the fraction of occupied states with respect to total number of states, total, okay? And we define this object here, this superscript dr, which means dressed, which is the dressing of a function. So it's like how the interaction affects a certain eigenvalue for a certain charge, let's say of index I, which with respect to the bare value, again, is dressed, modified due to the scattering shift with all the other particles. And notice that in this dressing operation, which is this is a linear integral equation, because you see the function, which is the unknown you want to solve for, it appears here and here. And here there is this n. N is also related one-to-one with the particle density, rho p, and the particle density identifies the state, because from the particle density we saw that we can compute all the conserved charges. So in the end, we had somehow at the beginning of the lecture, we had somehow the set of beta, which labels your generalized Gibbs state, which is in one-to-one with the conserved charges. Let's say this is, I think we denoted this way. Expectation over a generalized Gibbs state labeled by the inverse temperatures beta. And this is still in one-to-one with rho p, which is one-to-one with n. These are like equivalent system of coordinates that label your maximal entropy states. So you can uniquely define it if you give me all the set of inverse temperatures, or equivalently the charge densities associated to each of these. Let's say this is bar and this is bar. Or vice versa, you see that these charge densities are uniquely fixed once you have the knowledge of this rho by integration. So also rho uniquely identifies the state, or n equivalently, because they are related. So, and importantly, you see that every dressed operation feels the presence of the state, n. So these dressed functional are functional of the state you are. So it tells you that, for instance, the dressed eigenvalue for particle, energy, whatever, it's dependent on the state, because it's like the particle feels, a target particle with a certain momentum feels the effect of all the other particles due to scattering. This is why you have an integral. If you want to know this in momentum p, you also integrate on all the other momenta. Okay, it's not local in momentum because of this. Okay. And then this was everything for the thermodynamics part, and then we used this to construct. So let's say this is so you see in this blackboard is about thermodynamics, because everything is homogeneous and stationary, space-time translation invariant. There is no space dependence anywhere in this blackboard. Then we upgraded this to an hydrodynamic description, Euler in particular, Euler scale, using local density approximation. So in the local density approximation for weakly inhomogeneous systems, so let's say weakly inhomogeneous, inhomogeneous, and therefore local relaxation for a weakly inhomogeneous system. We saw in first lecture, when you have these inhomogeneities which vary over large enough length scales and are slow, we can use this assumption of local relaxation, so that our system is made by patches at each space-time point, xt, and each patch is at local equilibrium with its own temperature, inverse temperature. So the betas are upgraded to space-time dependent function, slowly evolving on some macroscopic coordinate x, space and time t. And because of this, you see then this chain, this function here, this rho p, also becomes a function of momenta, of course, but also space and time. And the same for all the other functions. And from this we derived, using also the expression for the current, which was something like this. this is the expression that we obtained last time for the current, where this V effective, this will be the first object that we define today to clarify its physical meaning. This is defined in terms of dressing. Dressing of derivative of energy, so the prime here means derivative with respect to the bare momentum. Okay? Let's say the energy, for instance, if you take a Galilean system, is something like p squared over 2, and P is equal, P of P is equal to P. Okay? So that you see this is like momentum dressed, E prime derivative of P squared over 2 is P, and this is 1, so this is like dressed momentum divided by, yes, 1 dressed. This is has the meaning of a velocity. And using these two ingredients, plus the ones from thermodynamics, we eventually derived this equation. I just repeat it because probably last time we ended up probably rushing here, so it's good to repeat. Yeah, please.
Rho prime rest is just one C prime.
Rho, what? This is P prime. And this is P, yes, exactly, is 1. So this is 1 dressed, which is written also above in the equation for rho here. Correct. And we obtain this equation. Okay? Now, first point, I mean, here I was just emphasizing derivative of x of the product. So both is V effective times rho, its argument acted upon by the space derivative. Now, this is an equation which, if you see, it has some physical meaning which is quite clear because it's like it has the structure. It is a continuity equation for the density in phase space. So at each point of the phase space, labeled by momentum and x, and it evolves in time according to this convective equation. Importantly, it looks simple, but it is not, because there is a lot of complexity hidden here, and can you guess where? Kind of, yes, because the point is that there is this velocity here appearing. This velocity, this effective velocity, is not the bare velocity of a quasi-particle, because again, there is dressing, there is scattering with all the other quasi-particles. So if you see from this definition here, the effective velocity is dressed, and therefore, because of the definition of the dressing, which is now the other way, above, it also depends on n, and therefore on rho. So this effective velocity, if you want, this is a of p, x, and t. This is a nonlinear, highly nonlinear, functional of the density itself. So it's a functional of rho, which is the unknown itself, and is nonlinear because to compute it, you have to pass through all these integral equations that define the density. This tells you that for an interacting model, the velocity is not bare, but it's dressed by the interaction, and therefore it depends on the state, rho, itself. Okay? And therefore this equation is nonlinear. So hydrodynamics of integrable systems is ruled by nonlinear equation. If you stay in the case without interactions, let's say you set the scattering shift phi equal to 0, you see that the dressing is just equal to the bare. So this velocity is just the bare velocity, which is p. And the p is state independent, is a simple function of momentum. So for a free system, this is not dependent on the state, neither on x and t. So you could extract it from the space derivative, and this would be a linear equation for the density. But for interactions, this is nonlinear, and this encodes all the complexity coming from this shift, scattering shift, and interactions. And since we did quite some work to arrive here, I think it's good to provide some further interpretation of this object, how it arises because of interaction. So first thing I want to do today is exactly this, so to clarify a bit the meaning of this object, these effective velocities, because it's of central importance in the equation. Then after this, we will do a couple of applications, so a couple of solutions of this equation into particular cases to get some more concrete view. And then in the tutorial, we do some other exercise after the break. Okay?
So the point of this V can be computed by assuming this thermodynamic Bethe answers.
Exactly.
From there, you can compute it.
Yes, exactly, because you see it's defined in terms of dress quantity. Dressing is an operation which is given by thermodynamic Bethe ansatz, but it's dressing xt, so at a specific point. So it's dressed on the state, on the co-moving fluid state, on the slowly evolving space x and t. So you have two additional variables, space and time, because this is changing, they are changing. It's a fluid which is moving.
So, right. So here, if I demand the steady state solution here, so for that, so how the statistics will come in? So del t, I will make this del t rho to be 0.
So then it depends on the specific case. We will see one case, for instance, for the steady state. Yeah, it depends on the specific initial conditions and the problem you study. Okay, I want to give some interpretation about the velocity. So V effective. In particular, I will try to convince you that V effective, I write it in words and then we see in formulas, but I think words come before because they are important, not to get lost in too many equations, is the large scale effective velocity of let's say the effective of P tagged quasi-particle with momentum P obtained No, they are interacting because they scatter. Yeah, the scattering shifts. Exactly, and now I just comment, the scattering shift, it accumulates. Due to collisions with other quasi-particles. So this is what I will just like to define. So in a sort, this is like you have, for instance, light. Light has a certain speed, right? But which in the vacuum has some value, which is 3 times 10 to the 5 kilometers per second. Now, if you put light propagating inside a medium, this velocity will be renormalized by the fact that it's propagating in a medium which is not free, where it can propagate freely. And I will show that this is exactly as the same kind of meaning, where if you have a quasi-particle propagating in a vacuum or in a free bath, where there are no interactions, this is like the bare velocity. So it's like the bare velocity of light. When it propagates in a bath made by all the other quasi-particles with which it scatters, this will renormalize the velocity given this effective velocity value. In particular, just to show you, it's something like this. Let's say these circles are particles which have some velocity. Hopefully I do it well. This is always a mess, but hopefully it's clear. Let's say you have a set of particles, which are these circles, schematized, which have a set of bare velocities, which is represented by the arrow. So this is traveling in this direction, this way, and that's it. Let's say we tag one particle here. Then remember that the definition of quasi-particle is the one of a velocity tracer. So it's a label which jumps from a particle to another such that the velocity you follow a certain velocity. So let's say this one in this scheme collides here, for instance, with this particle here. Okay? Let's say they collide, then this creates, in this case, a delay. They stay absorbed, and then this particle emerges with this velocity because they somehow swap velocities. Then, for instance, propagates a little bit again, and then it, for instance, collides with this one. Okay? Then there is a delay, and then propagates again with the velocity it obtains after the scattering. So it's like without scattering, its velocity, which is this white arrow, which is the bare velocity, will be the velocity at which this particle propagates throughout this medium, right? So it will just propagate along this line. Let's say, as usual, horizontal axis is space, and vertical is time. Okay, so it will propagate along this line. But due to the interaction, you see that if you look at large scale from far, because hydrodynamics is a large scale theory which doesn't resolve the microscopic details, what you see is that it propagates effectively around a different line with a different slope. And this different slope is exactly the effectivized propagation velocity due to the scattering, the shifts, these parts here or this part here, that this particle accumulates along the trajectory due to the fact that it propagates in a medium which is interacting with the other quasi-particles. Okay? Is this more or less clear, the level of intuition? I think this is nice because typically when one studies integrable models, one ends up doing a lot of calculations, writing many integral equations, and it's easy to get lost. So it's clear, it's good to clarify the physical meaning. Now, if you want to make a bit more quantitative this cartoon sketch, we can say that, for instance, the distance traveled by a quasi-particle, labeled quasi-particle with momentum, let's say, bare momentum P. So the distance delta x traveled in an interval dt will be equal to the bare velocity, which is E prime, so derivative of energy with respect to momentum. So let's say if the energy is p squared over 2, the derivative is p, okay, times dt. So this is like the velocity, the bare one. So it will propagate on a straight line without any other collision. Plus, there are collisions. So this sum n is a sum which runs over all the collisions taking place in the interval delta t of this. I think I abbreviate quasi-particle with QP just to make it short. Okay, so let's say this is the scattering shift, what we discussed also in the lecture 2, the one about the scattering theory, multiplied by -1 if the tagged quasi-particle with bare momentum P hits a quasi-particle on its right, let's say. So the +1 if it hits a quasi-particle on its left. Let's say, for instance, in the case of the rods, let's say this is the tagged one. We have done this drawing sometimes now. If I tag this particle, I am hitting another one that is on my right, and you see that the shift is on the right. Indeed, for the hard rods, phi is negative. It's minus the rod length, A. Okay, So you see -1 times a negative number, it's plus, so it's a positive shift in this case. And the interpretation, you see, it's quite clear. It's like E prime dt is like linear propagation in between collisions. And then there are shifts accumulated due to scattering. Of course, this is an equation which you have to take seriously, but with cum grano salis, because it's true at large scales when you look from far. Because first of all, if you have, apart from the hadrons, if you have a generic gas, particles don't propagate freely between collisions unless the gas is very dilute, because there is a potential, right? An interaction potential which makes trajectories different from linear, for instance, first of all. And second, it doesn't jump at collision. The shift is accumulated gradually as it propagates through the medium, okay? On large scale, when you zoom out, like looking at that trajectory, but from far, from the bottom of the room, you could describe it quite in this way, okay? So with a sequence of linear propagations punctuated with shifts due to scattering events.
Mm-hmm. So you're looking at the system you're looking at the post-grain version of the system.
At the
post-grain version of the scale. But if you look at the microscopic level, then of course these collisions are hampered by the statistics of the quasi-particles, right?
Yeah, indeed. The statistic of the quasi-particles indeed enters, because inside the dressing and the state there is also the function about the statistics, yes.
So I was just, so in this scale, there is no role of the statistics?
The statistics enters, yes, because the statistics, for instance, is determined to fix the initial state, which then dresses the function at the initial time, and then they are propagated forward, so this effect will propagate.
The distribution will be dependent on the statistics.
What?
The momentum distribution of the particles.
The momentum. The momentum, the dispersion relation, let's say, can be, it's like p square over 2 if you are not relativistic, or relativistic if you have a relativistic set. That one is, you can have, it doesn't depend on the statistics. You can have a boson and the fermions with the same dispersion relation. It's like if they are not relativistic, they both have energy p square over 2 bare.
When the swap is different, when they collide.
Then the collision, yes, the collision part, the scattering, that depends, of course.
That will come by a sign or...
Yeah, exactly. It depends on this phi. There is this phi which fills the statistics. Okay, then let's say we average over the density of particles in the gas, over the distribution of the particles in this medium, and what we get is something like this. Now I write the equation and I will give explanation of all the terms appearing. So by averaging, essentially we say that the slope that we see after all this collision is, we call it V effective, the time delta t. This is given by this equation which is obtained by averaging this, where I have to define now these two, which are otherwise undefined. So this S, P, Q essentially tells you this -1 or +1 depending on whether you scatter somebody on your right or left. So it's the direction of the jump. So for instance, it tells you that if you collide with a quasi-particle Q, that is, for instance, this is sine function. This is SGN. So it's +1 when the argument is positive, -1 when it's negative. So if you collide, target quasi-particle P collides with a Q, let's say that the velocity effective of Q is smaller than that of P, so that, for instance, you are colliding with somebody on your right that you reach because you are traveling faster. So this sign is positive. No, it's negative, sorry, because V effective of Q is smaller, so the sign is negative. and therefore here you get minus phi, which is minus tagged quasi-particle its quasi-particle on its right. So it's implementing this condition here, okay? So, and tells you whether you are jumping right or left, essentially, when you have a collision. And then there is the other bit, is this W, which is the probability, let's say, in a time interval delta t of hitting a quasi-particle with momentum q. And this is given by, of course, this object here, because of course this tells you that the probability of hitting for the tagged quasi-particle P another quasi-particle with momentum Q is proportional to the density of quasi-particle available at that momentum. So the higher the density for that momentum, the more likely scattering is with that momentum. And then there is this guy. This guy is a geometric factor, essentially, which in one dimension, it's simply the difference, because this tells you if P and Q have the same velocity, these two modes, so essentially they are propagating parallel to each other, so they will never collide, right? So this tells you that if P and Q are equal, this is 0, this probability is 0, okay? Now, if you insert this expression for omega and this expression for S inside the integral, what you get, so inserting this here.
So are you calling this dP delta t the second part or the total part?
Exactly. This word, what I call everything was, yes.
Are you calling this total thing derivative p into delta p?
The effective of P times delta T.
Total thing, because this E prime p into delta t, that's the initial part.
That's the part which, so you say I observe for a time interval delta T. So in this time interval I can possibly have, I have free propagation plus the effect of collisions occurring in this whole time interval, okay? And everything that I get out of this, I interpret it as a new slope, V effective, times the same time interval delta T, because I want to convert it to a distance traveled.
So this W thing you are defining the effective minus the effective P. Is there any mod or just bracket? Because you can
No, it's a bracket, this. It's not absolute value.
so you are calling it probability.
No, it's a, no, you're right, indeed. No, indeed, it's a modulus. It's a modulus because it must be positive. It was clear. Thank you. So yeah, that's absolute value. If you insert these two bits into the integral equation, you will see that you get this. I'm just plugging this and this inside that, and then the right-hand side I have V effective, and here I have this. Okay? So this is an integral equation, again. And what I want to say is that this integral equation, let's say maybe we can also do it because it's few steps, and then we pass to the other side. Let's say this integral equation, if you do simple manipulations, let's say, here, for instance, this product, you can split it in two. So for the first part, this V effective of Q, the second part, and then you can recombine the terms. This is actually equivalent to the definition of the effective velocity that we started from. There are some steps here, some simple manipulations of these integrals. I mean, few steps, it's 3 lines, but I just don't do it now because otherwise I think maybe we don't have enough time and it's just a calculation, so it doesn't tell too much about the physics. But what I want to convey is that this expression with this interpretation of the particles propagating in an interacting medium, which renormalizes the velocity of propagation, it's equivalent to the effective velocity definition that we obtained. Okay? So these two things, these right-hand side and these are identical, with few steps that you can find in the notes on page 24. It's 3 lines, not much, but I just keep it for brevity. Mm-hmm. Do you have comments, questions?
This
Please.
S and W, we wrote it in terms of some V effective minus V effective.
Mm-hmm.
But if we, is it like, of course it's true, but like, could we not use V effective there to make the equation simpler?
I think this was just done to give an interpretation of the formula we started from and to make it quantitatively. And then I think it's clear because you have to remember that these particles propagate with this renormalized velocity. So the collision depends by the velocity they have on that time, and the velocity is not the bare one as soon as you have a collision. So I think in the sign and the probability omega, you necessarily have to insert the effective one to make it consistent. Okay. So I think with this we more or less clarified the structure. Have you copied all? So sorry, maybe I was hiding it, but have you copied all the equation? Yes, I assume yes. I just wanted this because here we have the equation. Okay, so now we want to make a first application. For the application, I want just to say that here we have this equation for the density of particles. Okay, one can equivalently write an equation also for the total and the fraction n, okay? Because of course they are all related. In particular, I tell you, this I think it's related to one exercise, so we can see it probably in the tutorial later, explicitly, the calculation that for n, you get this equation. I write this because this is a bit more convenient to solve, and this is the one that we will now solve. This is the equation that you get from n. This is completely equivalent to that one, to the framed. I'm just writing it instead of rho p for n of p, that it's written here above, okay? And the advantage of this is that the effective velocity is outside the space derivative, so it's a bit simpler to solve. I think in the tutorial later we can do the calculation. It's related to one exercise together, how you pass from that one to this one. It's just a bunch of manipulations of the definition of dressing. So it's just, I would say, mathematics, not physical deep meaning. Okay, now we want to solve this for a specific case. We have 50 minutes, okay. So the first case I will discuss is called... This is out of the derivative. The space derivative is only on n. So the effective velocity is in front and multiplies. So the problem I want to study has many different names. It's called, let's say, Riemann problem, or partitioning problem, partitioning, or domain wall initial condition. There are many names, but they all mean the same stuff. And what is this? Let's say we have an Hamiltonian, okay, which rules the dynamics of our system. Let's say, to give a concrete example, we could, for instance, think about a spin chain, but we are not restricted to spin chains. and can be classical or quantum, we don't care. This is, for instance, the Heisenberg. I think this you have seen it in the course of Chiara, Heisenberg. Voila, yes.
This equation did you derive from this?
I didn't derive it, we see it later in the tutorial. I just say that if you start from this and you use the definition of dressing, some mathematical manipulations, you end up in this equation for n. The effective velocity, when you write the equation for n, is out of the space derivative. So just to say, this is one equivalent to that one, but a bit simpler because the effective velocity is outside. So this is, for instance, is the Heisenberg spin chain, where J is the coupling constant, okay? And let's say we want to describe inhomogeneous and non-stationary situations with hydrodynamics where there is transport. And the simplest inhomogeneity, it's the one of which is called here partitioning, which is like what you do if you have lived, if you've seen, for instance, in England, the bath is still the old way because there is not the temperature which can be turned with a single knob. There is one knob which goes with hot water and one knob which goes with cold, right? So it's the old way. And you have to turn both, and you have to mix cold and hot to produce something in the middle. And this is what we do now. Essentially, you partition your system in two halves. So let's say one which we can say left, and another one which we can call right. Let's say they are equal. Okay? So let's say, and for instance, this one here on the left, let's say is a thermal state with a certain inverse temperature beta left, okay? And the one on the right is another thermal state with an inverse temperature beta right, okay? So it's like you are joining two halves. One is hot, let's say one is cold, and therefore there is an inhomogeneity in temperature, for instance, in energy density. And this will drive some flow, of course. This is what you would expect, that, for instance, there is some flow from the hot part to the cold, right? There is some transport, some current. This is pretty intuitive, right? Do you all agree? Okay. So the initial state of this will be something like, this is density matrix, let's say, rho naught, so initial. It's equal to, let's say, e to the minus beta left edge left tensor product, e to the minus beta right edge right, divided by normalization, partition function. And let's say edge left and edge right this is a 1, even though it's not clear. And this is a right. Okay, so let's say these are two half infinite chains. Okay, so you have the one half infinite, so it's thermodynamic limit, so it's infinitely extended on the left, arrives up to -1, and this one goes from 1 to infinity. This is the Hamiltonian for the right part, and the left one. Okay? This is the initial state, this is why it's called also partitioning, because it's like you partition your system in two halves, which have some inhomogeneity, some gradient, initial gradient, so that then when you join them, when you mix, this gradient will drive some flow, okay? And how do you, this is, let's say, initial state, so time 0. Then how to merge them? Essentially, you connect the two halves. Puck. So then at the initial time you connect the two halves, you put them in contact so that they can communicate and there is some flow. Okay, some there is a minus J maybe, which I forgot. No, yeah. No, yeah, you're right. Let me see, this is -1. No, I have numbered it wrongly, I think, because you're right, sorry. So let's say after -1 there is 0, no? We all know. So it's -1, 0, and this is -1, 0. I would say. It's better.
The left part includes 0 and the right.
Huh?
The left one will have 0, right?
The left one, I mean, in principle is arbitrary the way I want to number. No, yeah, let me be consistent with this. Yeah, because this is from -1 and then there is -1, 0. Okay, this is from 1, so this is 1, 2. Okay, so let's say this is 0, this is 1. No, you're totally right. And then this one is, I made a mess. Then this one arrives up to 0, and this one starts from 1. Better. No, thank you. Should be fine, right? Yeah, because the left one arrives up to 0. J plus 1 for -1, which is 0. So, what we expect, right, when you therefore propagate in time this initial inhomogeneous state. Now, maybe on the blackboard is a bit more difficult to draw, but let's say you would expect something like, you would expect some flow, of course, between the two parts, and you would expect these to homogenize asymptotically in time, or as time goes on, to something in between, let's say. So something like, now at the blackboard maybe it's not it's not optimal the way I'm doing it. The coupling is the same. Yeah, here I think I set it to 1. If you want, you can put it also. So you would expect some homogeneity asymptotically. The way it's called also domain wall is because if you see this initial state, if you plot the initial energy density as a function of space, let's say, so the average, let's say, energy density, so it's Q2 over this initial state, this will be some left value. Then some right. Okay? And you see this is called the domain wall, this jump, discontinuity. This is also why you see domain wall initial condition. Energy density. It's like the standard convention we chose that number 2 labels energy 1, momentum 0, particle. Okay. So this is the expectation. So in principle, what would you expect for this at long times? So I'm just to say the total dynamics, then it's unitary. Let's say for a quantum system from the initial state. And we want to compute some observable, let's say some density current over this. Okay. I have not defined the total Hamiltonian, which is left plus right plus the link. This is how the dynamics is done, right? In the initial state, there is subscript 0 to say initial state. So it's like you have something on the left, homogeneous, something else, some other value on the right, and in 0, where you join them, which we have taken as point 0. In this case, I have done, let's say that the left one has more energy density. I mean, it's arbitrary. It's just one example, that one. In particular, the two can be also very far from each other. It's not linear response where you do some weak difference between left and right here, like green cubo. Here we can take arbitrarily different. Okay, so to build some intuition, what would you expect asymptotically here in time? Okay, so what would you expect for the current asymptotically? And then, yeah, indeed, in principle, asymptotically, maybe one could expect naively that it becomes, it could change that way, and then asymptotically, the current could become zero, because if this becomes homogeneous asymptotically, so let's say from hot and cold, you produce something in between, and zero gradient, asymptotically, zero current. Okay, because this is what we have in mind, I think, just to build some intuition, but intuition is not always good. It's Fourier law, right? Which is something that we study in physics courses, which essentially tells you that the current, J, let's say, of energy, so J2, is proportional to the gradient of the temperature, right? With a minus. So the current goes in the opposite direction of the gradient. So if you have hot and cold, it goes from hot to cold, right? And this is called, indeed, this is Fourier law or Fick's law, which tells you that, for instance, the current, J for a certain density, generic, is equal to minus some coefficient, which is positive, alpha, times the gradient of the associated charge. Okay? This is like Fourier law, heat law. Now, if you have, for instance, a conservation law, let's say d dt q plus dx j q equals 0, which is what we started from lecture 1 of the course now, and you plug this one here, what you will get is that d dt q equal to dx square alpha q. This is a q. There is no subscript. Second derivative in alpha. Exactly. So partial derivative in time of the density equal to transport coefficient times second derivative. And this is nothing but heat equation, right? It's what is very famous. Diffusion equation, whatever. To repeat? Yeah, the intuition is that if we, for instance, think in terms of Fourier law, that is something that we are mostly used to from high school and university, this Fourier law tells you that you get a current flowing in the opposite direction of the gradient. So the gradient goes from cold to hot, the current goes in the opposite direction, right? From hot to cold, to make it homogeneous, right? So you have that is proportional to minus the gradient of the temperature. This is, for instance, for the energy current. In general, for let's say for a generic charge density Q, if you have a Fourier law, its current will be opposite, alpha is positive, is a coefficient, is in direction opposite to the gradient of that charge density. So if I have a lot of that here and a little here, it will go from my left hand to the right. Okay? So this is like Fourier law. So we assume that by intuition we can think the current is related to gradients of the associated charge density. Then if you have a continuity equation and you plug this formula here for the current, you end up with this equation, which is the heat equation, right? First derivative in time equal to Laplacian, or second derivative in space. Okay? And let's say that the initial condition that we have, it's the domain wall that we wrote up there. So it's something like this. This big theta, this is a Heaviside step function, okay? So it's 1 when the argument is positive and 0 otherwise. And this is just the mathematical formula for that initial state that is up there, you see? So something on the left, x negative, plus something on the right, x positive. Okay? Now, if you see this equation and the initial condition, so this is the kind of problem we would expect to solve. It has gone exactly in the middle between the blackboard and the wood. It's unrecoverable. Okay, but if you look this problem here, what we can see is that both the initial condition and the equation, the heat equation, are invariant if you do this kind of scaling. Okay. So if you scale your solution x in space by square root of some positive number, capital A, and time by A, you see that the initial condition is not changed, and also the equation is not changed. Of course, the scaling is not surprising, right? Exactly, yeah, if you want, yes. And if you want, this is zooming out in a diffusive way, right? Because this tells you that squared x squared over t, it's constant. You are looking at you look at space-time point scaled such that this combination, squared space over t, is constant. And this is the typical scaling of diffusion, where you have space squared time linear, right? So the dynamical exponent is 1/2. And this is, of course, true for that equation. Now, if you have this kind of solution, so from this invariance, we can say that the solution will be some scaling function, capital F, of x over square root of t. Fine. Now we know the current is the gradient of Q, so we can take the derivative.
F of 0 is Q at x.
What?
F of 0 is Q at x over 0.
I didn't understand the question.
Initial condition.
Ah, the initial condition is that one, this one here.
F of 0 has to be that.
Is invariant as well.
No, F of 0 has to be that. Yeah, this is the one.
No. This is like the solution at a space-time point xt.
Like if you put x to be 0 there, t to be 0 there,
Uh-huh.
that is coming simply.
Yeah, but this is for the time evolved one. It's then for the initial state, I'm saying that also the initial state satisfies this kind of scale invariance relation. In particular, yes. I want to say that then, if you take the gradient of this and you act on that, you will see that you will get, by chain rule, something like this. If you take derivative in space, you have this, so you will bring out 1 over square root. Sounds? And for long times, this goes to 0. Sorry.
Scaling, but how QXT scales as this
The way I motivated is that if you look both at the evolution equation and the initial condition, they are both invariant under this scaling of space and time according to some positive number. Therefore, if both the initial condition and the dynamical equation are invariant under this scaling, we can take the solution to be a scaling form of you see x squared over t constant, so x over square root of t. And then I'm saying that if you use the equation of state from diffusion, so from Fourier law, the current is the gradient of the density. If you apply the gradient, you see if you take a derivative in x, chain rule, you will bring out a factor 1 over square root of t. And therefore, for long times, this decays eventually to 0. Okay? of course, this is the mechanism of diffusion, because if you have an initial inhomogeneity, for a long time this will tend to flatten more and more, and when you are in some asymptotically, let's say, equilibrium state at a temperature in between the left and right initial ones, there is no gradient anymore and nothing flows anymore, okay? Now we want to see how this is different for the case of integrable systems that we studied. So in particular, we start from this equation, from the equation that we wrote before. This is the same equation we wrote before, so this is applying now
model, you showed that, Heisenberg model, you showed that this Fourier current actually comes up, and then we have this.
I'm not only for the Heisenberg. Heisenberg was just to write you an Hamiltonian at the beginning for reference. I would say that generic model, if you assume Fourier law to be valid, asymptotically you get no current.
And how to use this Thermodynamic Bethe answers here?
This is what we do now. How to instead solve it properly with the Bethe ansatz, with this GHD expression. Exactly. So we have this stuff, and then we have the initial condition, which is something like first argument is P, then there is space in my notation and time. So this is, again, our step initial condition in homogeneous with a step jump in 0. And you have a state on the left and a state on the right. Let's say you want a thermal state on the left and right, so two temperatures. This means that your state will be described and can be computed by the thermodynamic Bethe ansatz. This equation here, where here for this W you put for the left-hand side beta left, so inverse temperature left, for the right-hand side, inverse temperature right. This actually, the tutorial later we do it. We see it directly from numerical solution, how does this behave. Now I explain you in general. Then later we see a concrete case so that it's clear. But just to say, these are two occupation functions which can be obtained from the thermodynamic Bethe ansatz of the state labeled by the multipliers left and right. And this gives our step initial condition. Now, notice an important difference now, which immediately comes. Diffusion equation here. This is useful, actually, this rod. The diffusion equation here, you have first order in time and the second order in space, okay? Here you have instead first order in time, first order in space as well. So the scaling of space and time is different. This is not surprisingly, I would say, because Euler hydrodynamics indeed is an equation for an unviscous fluid, a fluid where there is no viscosity, and describes ballistic convective propagation of fluid modes. And ballistic means that space and time, like in relativity, scale together with the same exponent, which is 1. This is why it's first order in both, and this is a crucial difference, because you see now that this equation, the initial condition, and the evolution equation are both invariant if you take space and time and you scale it, let's say with some parameter lambda x and t, which is positive and let's say large, which is the Euler scale. If you do this kind of scaling, you see that the initial condition is unchanged again, and also this equation is unchanged because it's first order in space and time. So now I am scaling with the same number, so that the ratio x over t, which I will call, now this is the difficult part because I don't know how to write it, but this is xi, I hope it's clear, so that the ratio x over t, xi, is fixed, okay? In particular, this is called, a given value of xi is called light ray in the space-time diagram. The second application, we do it probably in the tutorial, but fine, it's good to go slowly. Okay, so this is, for instance, a certain light ray in the space-time diagram. So it's a line. On this line, the ratio x over t is constant, and it has some value. Okay, and let's see that this is like our left. This is our right. Fine, and here in 0 is where they are connected. Please.
Oh, this is the initial
State. Yes, orange, blue.
And what are you representing?
With this, I am representing a line in the space-time diagram where the ratio, so on this line, the ratio x over t is constant. And from this scaling argument, we know that the solution is going to be a scaling function of the ray only coordinate. Of course, this for sufficiently long time. This also maybe relates to your question before. You were asking me about the time equal 0 in the scaling. Of course, the scaling is valid for large enough time, because for small times, you will have some microscopic contribution. Remember, hydrodynamics is something for weakly inhomogeneous setup. At the initial time, this is by far not weakly inhomogeneous, because it's the sharpest possible discontinuity you can have, is a jump. So it's not inhomogeneous. So this tells you that for short times, you will have some microscopic dynamics going on. Then for sufficiently long times, in particular for integrable models, you see it's very fast, this domain wall state will become smoothen, will smoothen a bit, and this is the regime where you have a smooth inhomogeneity, and this kind of equation applies, and this scaling argument applies. Okay? This is also related to what you were asking before. So the scaling argument is valid for a sufficiently long time, so not only for 0. It's clear. And then you can write this scaling form for the solution. Is this clear for everybody? Okay. Then, if we do this scaling form, in the equation above, we get this kind of equation. Yes, I have inverted the order of the variable, fine. It's equal to 0. So I'm just saying that you write this partial differential equation that you have on top is space and time in terms of the variable x over t only, because you have this scaling form, and this is becoming this form here, where this derivative here is with respect to xi. And the n is a function of xi, the light ray, x over t only, and the momentum. Is it fine? Okay. And then you can see that essentially what do we expect? Also, what do we have? We have that initial condition, right? Negative, x negative left, x right, at right. So we have this equation with the boundary conditions that tells us that if xi is going to plus infinite, so it means far on the right, right? Correct? So this will approach the right boundary condition. If psi, on the other hand, goes to minus infinity, this will approach the left boundary condition.
I didn't understand this one because
I mean,
it's the initial condition, right? But when psi is going to plus or minus infinity, the time equals to.
let's say you fix some time, okay? So I mean, if x is very large and positive, so on the right, xi will tend to, t is positive, is time, from 0 to something. So x can be either positive or negative, right? Whether you are right or left. So if x is positive and tends to plus infinity, so this means that the ray is tending to plus infinity, it means that you are approaching the state here far on the right, this reservoir on the right. So your state should match the initial one on the right. If you go infinitely far away on the right-hand side, this is the same stuff, but infinitely far away on the left-hand side. Because of course there is the physics meaning is that this inhomogeneity is localized in 0, right, initially. Of course, information propagates with some velocity which is finite. So from here you can expect that this inhomogeneity will start flatten more and more, and will expand as a function of time, but with a finite velocity. So if you take thermodynamic limit, infinitely extended chain on right and left, the far right and left will not be affected, and they act as reservoirs which inject or extract particles from the central region, creating eventually a stationary state in the central region. This is the interpretation. This is why also this protocol is particularly interesting, useful, because it's a simple protocol where you use essentially the system on its own, the far right and left reservoir act as bats that drive the central part of the system into a non-equilibrium stationary state, as we will see. Okay, and these are boundary conditions. So this is a partial differential equation. You want to solve it with some boundary condition. And now you see that essentially, yes, I'm just thinking, actually I have not derived, there are 2 or 3 steps which I have not done, but I'm just saying, I take this n of p, x, and t to be a scaling form of x and t like this, where psi is the light ray, x over t, and then you can see that you do chain rule, so you convert the derivative in time into the derivative in psi, the same for the derivative in space, and in this way you get a differential equation in terms of the variable psi only. You do chain rule, for instance, here, and in this way both time derivative and space derivative are converted into a psi derivative. And then you have this factor here which comes from the chain rule. It's a simple way. You take this partial differential equation and you write for the scaling function.
I understand the xi can goes to plus infinity and minus infinity to match the boundaries. The question is, we are calling the xi to be the light cone, but conventionally we have the xi to be 1, right? For the light cone, it cannot exceed 1. So
This is a good point. Depends on the model, I would say, because now I'm going to comment about this. Because yeah, you have anticipated that there is a light cone, even though now it's pretty clear. But yes, I want just to say that when you solve this equation, you see that in general, if this term here between the round brackets is different from 0, the only way this can be equal to 0 is because this derivative is 0. Okay, so this tells you that this n as a function of psi is constant everywhere, but on values psi star, let's say, which are functions of p, which satisfy the following equation. If psi star, if you have a specific value, let's say of psi, which we call psi star, which is a function of momentum p, such that this equation is verified, you see that this term here in the brackets is equal to 0, therefore the equation is satisfied and this derivative can be non-zero. You can have a jump on array of the solution. Otherwise, if this is not verified, this is not 0, and you need to have n constant. And therefore, this we can write it as n of xi and p as we can write the solution of the equation in this form, you see? So every time xi is equal to one of these xi star values, which are functions of p, you have a jump. So you have a theta, an heaviside step. And this, in particular, you see that for xi infinity matches the right boundary condition. For xi minus infinity, it matches the left one. And every time you have a jump for a certain specific values of xi star, your solution essentially changes, interpolates from left to right. I'm saying that, yes, sure. I'm saying that from that equation, you see that when you have this xi star, you can have a change, a discontinuity in the equation. Otherwise, this n is always constant. So I take essentially a discontinuity, theta heaviside step function, centered at xi star, which tells me how I jump from the right, which is for plus infinity, or the left, which is obtained for minus infinity in this. In this way, you have this solution satisfies this boundary condition, and at the same time is constant everywhere, except at the values of xi equal to xi star. Is this clear? Is it better?
The current is homogeneous, the current is constant, 0.
When?
After a long time.
This is what we saw before with diffusion.
Yeah, but the number density is not. I mean, it's a...
This, yes, with diffusion you can have some non-zero density, but at zero current, asymptotically for long times, yes.
But this inhomogeneity is maintained, right? I mean, we can have, at the right side, we can have some different current number density than the...
Yes, yes, yeah. In general, exactly. Now what I want to say is that, first of all, in this way, with these two equations, you have now a prescription to solve the problem, because to fix the solution, I mean, these two are fixed by the initial condition, right? So let's say you know them. You need to fix this xi star. So to determine xi star, you have to solve this equation. But the V effective, which is written somewhere here, it's determined by dressing, right? Dressing contains n. And n is the solution itself of the equation. So you have to do it this iteratively. It's a self-consistent scheme. Essentially, you start from some, let's say, initial guess, for, let's say, for instance, the velocity. For instance, for the velocity, we could take as an initial guess the bare velocity. So you start to say, my initial guess for the bare velocity is this, for the effective velocity, the bare one. Using this, I solve this equation for xi star, so I get an initial guess for xi star. Let's say I put a subscript 0, which is, let's say, iteration 0, so initial guess. And then, so from this xi star, let's say at iteration n, I will compute my state n. Let me use m because n is already here. And then from this, I will compute the effective velocity. And from the effective velocity, I can close back and recompute psi. Right? Because, so from an initial guess, I compute n from the formula. From the n, I compute the effective velocity, dressing operation over there above. From the effective velocity, solving this, I will get a new value for psi star. And then I iterate. So you do this iteration scheme until you converge. This is exactly the tutorial. After the break, we will do this so that we see on a screen the solution of this problem. And what I want to anticipate in the last 8 minutes is this clear, the way to solve it? Okay. What you will see is that essentially you get something like this. The solution is a function only of the ray, is a function of the ray only, and will be something like this. Now I sketch it in a more or less qualitative way. So there is a light cone forming and opening from the junction of the two halves of the system, such that essentially asymptotically here, far on the left, the information about the inhomogeneity, for instance, for a given time, has not yet reached. So let's say you look at a fixed time slice. And so here you still have this asymptotic state left. Here, same discussion on the right. In between, you have some profile forming, which interpolates between the two, okay? And in particular, from the, and this is a light cone, just to say. So it's a causal propagation in time of the information about the initial inhomogeneity, which propagates with a certain speed, which is finite or infinite, but still you can get it. And outside it, you still see the asymptotic thermal regions. Inside, you establish some non-trivial, non-equilibrium flow profile of currents. And in particular, you can look that for psi equals 0, if you compute your solution in psi equals 0, you see from this equation here, psi equals 0 means, let's say, fixed time, fixed space, and very large time, okay? So it means that you are looking at a stationary state. And this is a non-equilibrium stationary state, which is this acronym, non-equilibrium stationary state, because, as we will see, it's a stationary state which supports the flow of a current. So in the stationary state, the current will be non-zero. On the ray psi equals 0, there is a non-zero current, differently from the previous case, the case where we had assumed diffusion. So this means that transport indeed is ballistic, is not related to gradients of profiles, because these modes are convectively transported by Euler, and therefore it allows to produce a stationary state which supports the flow of a non-vanishing current, even for long times, even in the absence of inhomogeneities, because at long times profiles tend to flatten. This is the main message I want to give. I mean, let's say, think for large enough space-time coordinates when this scaling argument applies, okay? But yes, it means near the junction. It means x equals 0 if you want. And of course, because this, the light cone propagates from the junction. So it starts from there and then it expands. And it opens up as a function of time, because the more you wait, since it is a function of psi, if you have some behavior at some time, then you will see the same behavior at a larger space coordinate x for a larger value of the time. This is what determines this light cone scaling form appearing. Is it clear? Is it better? I think it's 57. I don't know if I can do something else. Or maybe, no, maybe I think it's good to stop here because I see it's 10:57. So let's say we have a break and then we start, then we have tutorial anyhow after that. In the tutorial, I think then since we arrived here, it's the good natural point will be now to see the solution of this in one specific case. And then I give you also another solution for another protocol of the hydrodynamic equations, and then it's open for questions, any questions you can have about exercises or anything. Then we resume in 30 minutes.
Let us thank the speaker.